right, good afternoon. Welcome back. Hey. All right, so my plan today is to go over homework 1, which I graded and posted some comments on Canvas for you. So I want to just run through that really quickly and then start talking about logic and propositional calculus and all that good sort of stuff, which will be the next week and a half of this course. And it's mostly chapter 3 from the textbook. So that's where we'll be spending our time. So any questions before we get into that? All right. Well, so on the homework, so let me pull it up over here. So I mainly looked at section 1.1, question 2, and section 1.2, question 4. So 1.12 was looking at the basic construction of sets and using set builder notation and things like that. So let me pull this over here. So 1.1 question 2, list all the elements of the following sets, and there were 5 sets in there. And the only ones that really gave people some issues were 3 and 4, or C and D. So C says the set of all negative k such that k is contained in the positives. And when you see a notation like this, right, the way to think of it maybe is the set consists of all of these things such that that stuff is true. So if we want to use this to construct a set, we can pick any k contained in here, and we're told that minus k is in the set. So for example, p is the set of all positive integers, so k could be equal to 1, which means our set contains negative 1. K could be equal to 2, which means our set contains negative 2. K could be equal to 10, which means our set contains negative 10. And after you do a few of those, you get the idea that basically this contains all of the negative integers, which we could write sort of informally like that, right, assuming we know what the ... means. Or we could write it as the set of all x contained in the set of integers such that x is less than 0. And that also works. A few people thought that this was the empty set because there are no elements in P which are negative, right? But that's not the right way to think about this. Think of it as the statement that, you know, this is the set consisting of all of these things which satisfy this property. And there are k's that are contained in P, but for any of those, the negative k is in our set. A few people also suggested that this would be equal to something like this, or negative this, or negative that. And those are right in spirit, but wrong in a rigorous sense. So this isn't well defined. We don't have a notion of negating a set, right? Same thing with this. And this is a very strange kind of set. It's a set containing another set. This set has one element. Okay, the one element in this set is P, the set of positive integers. So that's a totally different thing. But we can write it like that, or we can write it like that. All right, and then question 1.1, question 1, question 2, part D. So the set of all n squared such that n is -2, -1, 0, 1, or 2. So again, n can take on any of these values, and for each of those values, n squared belongs to our set. So if you just write that out, you're going to find these things in your set, but don't ever write a set like that. Okay? When you list the elements of a set, they should only appear once or 0 times in the set. So you could write the answer for part D like that, and that would be fine. But if you put the 4 in twice or the 1 in twice, I made a note about that. All right, on question E, you're looking for positive integers which are factors of 24. So a factor is something that divides. Okay, we'll talk about that in detail when we go on to number theory. But a factor of 24 means something that divides 24, which would be for positive integers 1, 2, 3, 4, 6, 8, 12, and 24. So there's 8 factors. All right, the other question I looked at was question 4 in 1.2. And we talked about this some in class, and I made a note in the assignment on Canvas as to how these should be done. So our universe is the set of integers from 1 through 9. And I'll move this out of the way in a second. And we're asked to pick sets A, B, and C, which are from this universe, to illustrate the following facts. Okay, so the first fact was if A is a subset of B and B is a subset of C, then A is a subset of C. And this one is a little hard to show with a lot of rigor because it's sort of so obvious. But you could do something like this. Let A equal this set, B equal this set, and C equal that set, right? A is a subset of B, right? B is a subset of C, and A is a subset of C. And there's really not a whole lot more to write for that, right? I mean, I could explain why A is a subset of B because A contains only one element 1, and that's also contained in B. But it's really just an illustration that, you know, at least for these particular A, B, and C that I picked, A is a subset of B, B is a subset of C, and hey, guess what? A is also a subset of C. So that one's confusing perhaps because it's so kind of obvious that, you know, this transitive property applies. But the goal was to pick particular sets and then, you know, see that this is true. This, given this and this also applies. All right, so for question B, we're asked to show that A minus B is not equal to B minus A. Okay, so this is not subtraction as in the case of numbers. It's a set operation, and our sets might not have numbers in them. They could be sets of letters or you know, types of foods or whatever. So this is complement. This is the complement of B in the set A, or if you like, it's A take away B. So start off with A, throw away everything that's in B. And yeah, someone asked if we can go over question 8. We can do that. So this is A take away B. So show what your sets are. So I'm just going to use the same sets. Let's let A be the set 1 and B be the set 1, 2. All right. A minus B is A with everything that's in B thrown away. So start off with A. If there's a 1, get rid of that. If there's a 2, get rid of that. This is just the empty set, right, which I'll write as that. B take away A says start with the set B, throw away everything that's in A. So if there's a 1, throw that away. This is just going to be the set 2. So that's what B minus A is, and I can simply note that's not equal to A minus B. So that's a demonstration again. It's not a proof, right? Because in some cases this will be equal to that. But for particular a and b that I've chosen here more or less at random, I've illustrated that a minus b is not the same as b minus a. All right, part C, if A union B gives you the whole universe and A intersect B is empty, it follows that A is equal to U minus B. So, so here again, let's pick some sets A and B, but we're required to pick them so that their union is the universe and the intersection is empty. So let's do something like let A equal 1, 2, 3, 4, 5, and B be 6, 7, 8, 9. So I'll note what the union is that which is equal to the universe. I'll check the intersection. Well, is there anything in common between these two sets? No. That's the empty set. Okay. So we have picked an A and B which correspond to these requirements. The universe is the union and the intersection is empty. And we want to show that A is equal to U minus B. So U minus B equals right, that thing minus that thing, which is equal to, we'll take this whole set, throw away 6, 7, and 8, 9. What do you get? 1, 2, 3, 4, 5. And sure enough, that's equal to our set A. So that's an illustration that that this property applies, at least in this particular choice of A and B. All right, and then the last one was show that A crossed with B intersect C equals A cross B intersect A cross C. All right, so I asked you in the write-up to pick interesting sets, but not too interesting, right? Cross products blow up with the size of the things you're taking the product of. So if I have 5 elements here and 4 elements here, I'm going to end up with 20 elements in my Cartesian product. I don't really want to do that. So I'm going to pick some simple sets. I'm going to set A equal to the set 1, B equal to 2, 3, and C equal to 3, 4. Because I don't want any of these cross products to get too big. All right, so we're going to demonstrate this. So first I have to figure out what B intersect C is. And the only thing in common between B and C is just 3. All right, so A cross B intersect C equals the set 1 crossed with the set 3, which is equal to just the set containing a single tuple 1, 3. And I'm going to underline that. And now I'm going to calculate what the right side is equal to. A cross B is the Cartesian product of this singleton set and this set containing 2 elements, which is going to be a set containing ordered tuples where the first element comes from A and the second element comes from B. And there's exactly 2 of those. And then I'll do A cross C. And I'll get another set containing 2 ordered tuples, 1, 3, and 1, 4. And now I'll take the intersection of these 2 sets. And the only thing in common, this has 2 elements, this has 2 elements. The only element in common to both of these sets is 1, 3. So that's what the intersection of those 2 is. And that is equal to the Cartesian product of A with B intersect C. So we've shown that this equality holds for these particular sets A, B, C. So that's just, you know, getting your hands dirty, actually playing around with some sets and doing these operations, getting familiar with what they look like. Okay, again, not a proof, but a demonstration in a particular case. All right, yeah, and a few people found out the hard way that if you make these sets too big, you get really, really long Cartesian products. Basically, if A and B have m and n elements, the Cartesian product will have m times n elements, because that's how many ways you can take one thing from the first set, one thing from the second set. All right, someone asked about question 8. So question 8, so we have these sets defined in the previous question: the set of all students at a school, number of day students, math majors, graduate students. And in question 7, you draw Venn diagrams to sort of ferret out what these types of sets look like. So non-math undergraduate students would be students who are not math majors, so outside of M, and also undergrads, so not graduate students. So it would be the union of the complement of M with the complement of G. So you play around with that to get a feeling for what these sets look like. And then question 8 asks you to run some numbers. So if the whole universe is 16,000, number of day students is 9,000, math majors is 300, graduates is 1,000, number of day students who are also math majors is 250, etc., 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 as Yul Brynner would say. So, so let's just spec this out a little bit. So the universe is 16,000, day students is 9,000, math majors is 300, graduate students is 1,000. Number of day students who are math majors. So that's day students and math majors is 250. Number of day students who are math majors is 250. 50 of whom are grad students. I'm not sure about the wording here. Also assume that the number of day students who are math majors is 250, 50 of whom are grad students. So, day students and math majors and grad students sounds like 50. And then there are 95 graduate math majors. So, graduate student and math major. We've got 95. And total number of day graduate students is 700. So if you're day and graduate, you've got 700. All right. And then we're asked to find the number of students in these different categories. So evening students means you're not a day student. So if you're a university student but you're not a day student, and that's just going to be 16,000 minus 9,000, so that's 7,000. And I don't know if we can get to the last one without getting through the earlier ones. Non-math majors. So non-math major is someone who's at the university but not taking math, which is 15,700. Number of undergrads is someone who's not a grad student, so that's a university student who's not a grad, which is 15,000. Do they talk about principle of addition, subtraction? Talk about symmetric difference. They don't. Okay, so we're just going to fake our way through this. So we want daytime, graduate, non-math. So you need to be a daytime student and you need to be a graduate student and you need to be not a math student. So, let's see. I may defer on this and come back to it later. We're given a quantity for math day grads. Yeah, math time day graduate students, we have 50 of those. So if we know how many daytime graduate students we have, which we do, is 250, and we know 50 of those, daytime graduate students is 700, and we know that we have 50 math daytime graduate students, so we have 650 daytime graduate non-math students. But I'm not liking this problem right now because it's a little hand-wavy the way we're going through this, right? And there's something called the principle of inclusion-exclusion that we're going to get to, which lets us formally say how we can calculate this, right, from this and that. So let me defer this. Let me think about this and see if there's a way to do this more formally with what we've gone over so far. And I will throw together a short video about this and post that up. Or I may say let's wait and come back to this when we get to principle of inclusion-exclusion. But I think you can fake your way through this intuitively, but I don't really want to do too much encouragement of doing our intuition for this kind of stuff. So let me come back to this. Let me look at what we've done and where we're going, and then, like I say, I'll post a video and tell you about it Friday. All right. What else? All right. So let's start talking about logic. Or logic. There we go. All right, so we're talking about propositional logic. And if we're going to talk about propositional logic, we have to know what a proposition is. Okay? And this is possibly the most important definition of this entire section. And it's a fairly benign sounding definition, but you're really going to want to write this down somewhere and refer back to it. Every time we do something with propositions, put this definition in your head. Okay? And I'll tell you why in a bit, but let's write down a proposition. So a proposition is a declarative statement that is true or false. A proposition is a declarative statement that is either true or false. All right, and let's do some examples. So over here we'll list some good propositions. My name is Nick. It's a declarative statement that has a truth value. That's a good proposition. 1 + 1 = 5. That's a good proposition. It's a declarative statement. It's saying if you take 1 and add 1 to it, you get 5. It doesn't happen to be a true proposition, but it is a proposition. We are in CSE215. That's a good proposition. If today is Tuesday, then we are not in CSE215. That's another proposition. It's a declaration. It has a truth value. All right, we're going to change 1 plus 1 to actually equal 5. Cool. We got 3 votes. Yeah, it's a law now. We can develop a system of mathematics based on this and probably get some interesting stuff. All right. Let's put down some things that are not propositions. Hello. It's not a proposition. What is 1 plus 1? It's not a declaration that has a truth value. One plus 1, not a declaration that has a truth value. X squared, not a proposition. What would be a good proposition is this. An equally good proposition is this. That one happens to be false. But it's still a proposition. Okay? Whereas this or this or this, those are not propositions. They're not making a declaration. They don't have a truth value. Okay, this sounds pretty straightforward. Why am I beating the point so hard? Because the number one mistake that we'll make when we're writing proofs is writing things that are not propositions. And when we write a formal proof, every statement we write is going to need to be a proposition. It's going to need to be a declarative statement that has a truth value. And inevitably, we're going to forget what we're doing, and we're going to start writing things like this or that. And when I grade it, you'll see a note saying not a proposition. Okay? So this is something we're going to have to come back to again and again. So we always want to be writing propositions. So we got to keep in mind, proposition must be a declaration of some sort that has a truth value. All right, well, if we have a proposition, we can have a propositional variable. So we can use, so a propositional variable is a symbol that represents a proposition. So for example, I can say let P be the proposition 1 plus 1 equals 5. And for now, when we're writing down propositions and we're using a variable, I'm going to ask you to be very explicit and do something like this. Let P be the proposition 1 plus 1 equals 5. That's absolutely clear. P is a variable. It represents a proposition. This is the proposition it represents. Clarity is really important in this subject. Okay? This is a subject about logic. We're looking at ways that we can make arguments and prove or disprove things that are undisputable. That anybody else who understands logic can look at what we're doing and come to the same conclusion that we're coming to. So there's very little wiggle room here. So let me show you a poor choice of notation. You're writing a proof and you say P colon 1 plus 1 equals 5. Okay, don't do that. Because what does this colon mean? Well, maybe it means P such that, or maybe it's a grammatical mark. But it doesn't unambiguously mean let P be the proposition that 1 plus 1 equals 5. Okay? It's sloppy. Okay? Let me show you what I never want to do. I'm going to have to burn this paper after I write it because this is so evil. Don't ever do this. Okay, P equals 1 plus 1 equals 5. That is mathematically meaningless. Because this is saying P is equal to 2, which is equal to 5. That has no business on a proof. Okay? And this is not what I meant. I didn't mean P is equal to 2, which is equal to 5. I meant P is the proposition that 1 plus 1 equals 5. But this equal sign has very specific meaning. Right? Don't ever write something like that on a proof. You get an instant frowny face from me. Okay? And it's pretty obvious, you know, if this is my proposition, 1 plus 1 equals 5, that this looks funny, right? But if P is the proposition that it's sunny outside, right, you might try to write something like P equals it is sunny outside. Well, don't do that either. Okay? Because now I've set P equal to a sentence, right? And we really mean P is a proposition which says it is sunny outside. P is a proposition which says 1 plus 1 equals 5. Okay? So don't do these things. Spell it out. Let P be the proposition that. Okay? It's another point I'm beating to death, but again, this is something that will come up again and again in homeworks, quizzes, tests, exams. Okay, and you end up losing points. And it's not just being dogmatic. There's cases where you'll start doing this and it will lead your thinking down a bad path. And you'll end up doing things that aren't logically correct, but are mathematically correct. And you get to the end and you think you've got a good proof, but logically you don't. Okay, so let's be very strict in how we describe propositions. So propositional variable is a symbol that represents a proposition. And there's two special symbols that we reserve for particular kinds of propositions. Not really propositions, but truth values. So T and F. T we use to represent true, and F we use to represent false. And true, it's kind of a bit of a stretch to say it's a declarative statement, but, you know, true, it's a declaration that is absolutely true, and false is a declaration that's absolutely false. So those are sort of primitive propositions, and we reserve the symbols T and F for true and false. All right, so all of this lets us talk about propositional calculus. What is calculus? Calculus comes from a Latin word for pebble or stone, which was used for calculating, right? So calculus is kind of a general term for calculating or reckoning. And so we can do, you know, calculations using propositions. And this is a very old subject. This goes back at least to Aristotle, about 300 BC, studying the nature of propositions and what we can do with them. And one thing we like to do with propositions is build new propositions from old ones. That's kind of where math comes from, right? When we talk about defining addition or multiplication or trigonometric functions, we're describing ways we can come up with new numbers from old numbers, right? But not just willy-nilly, here's a number, give me another number, think of something random, right? When we square a number, we're doing something very specific. So we're going to look at very specific ways we can create new propositions from old propositions. And we'll get into some good symbology now. So one way we can do this is negation. So throughout all of that we're going to talk about this afternoon, I'm going to assume that P and Q and R and maybe some other things are, let these things be propositions. And I'm not going to worry about what propositions they are in particular, but we'll use some examples where we'll plug in specifics for these. So given a proposition P, we can write a new proposition, which is this funny hook symbol followed by a P. And this is a proposition, which means not P. All right, so this is a symbol for not P. So if P is the proposition that 1 plus 1 equals 5, not P is the proposition that not 1 plus 1 equals 5. All right, let P be the proposition 1 plus 1 equals 5. Not P says, literally it says not 1 plus 1 equals 5, but that's not how we talk normally, right? So we would actually say this is the proposition 1 plus 1 is not equal to 5. But we kind of need to know how the language works, how the English language works, to understand that not this thing is the same thing as saying it's not true that 1 plus 1 equals 5, which is the same thing as saying 1 plus 1 is not equal to 5. And this gets into one of the subtleties about this subject, which is language issues. So English is a really imprecise language, right? It's got all kinds of weird rules that really make no sense. They're just rules, right? So the way that you form a sentence, the way you make a plural, the way you make a possessive, a lot of this stuff doesn't follow a rule. It's just the way things are done. It's one reason English is such a hard language. And there's a lot of imprecision in it. And so, in some languages saying not this would make perfect sense. In English, this doesn't really flow as a sentence, not 1 plus 1 equals 5. So we have to change it around. Propositional logic is very precise, very rigorous. When I say this, it means the negation of P. It means if P was true, this statement is false. If P was false, this statement is true. So part of what we're doing is we're working with propositional logic because it's very clean and very precise and very rigorous. But sometimes getting there from English can be tricky. To a lesser degree, getting from a rigorous statement in propositional calculus back into English can be tricky. Usually not as bad. The bigger challenge is sometimes when we think about things in English, it will lead us wrong. It will suggest something which is not rigorously what we meant. And I'll give you a really quick example. Super salad. You go to a restaurant and the wait person comes over and says, "Would you like super salad?" From a propositional calculus standpoint, the correct answer is true. I would like either soup or salad. Okay, that's not the question. The question is, which would you like? From a propositional logic standpoint, the answer could be both. From the restaurant standpoint, that's not possible. You have to choose one. It's an exclusive or. But the waiter doesn't say, "Would you like soup, X, or salad?" They say or, and we understand it's got to be one or the other. Okay, so super salads, yes. So there's imprecision in spoken language, written language. So part of our challenge will be navigating that and getting over to the realm of propositional calculus. Once we're in this realm, things are nice and clean and precise, okay? But it's always a bit of a challenge going back and forth between those. All right, so making new propositions from old ones. One way to do that is negation. It's this funny not symbol, and it says, this is not whatever you said. So if my proposition was my name is Nick, then the negation of that is my name is not Nick. Okay? It's still a good proposition even though that proposition is false. Okay, but you start to see that if a proposition P is true, the negation is going to be false. And if a proposition P is false, like it's raining right now, the negation, it's not raining right now, turns out to be true. Okay, and this is exactly how negation works. And we're going to write truth tables for this in a few minutes. And this is all Engineering 250, right? It's the same stuff over again, just some different language and a different domain that we're working over. All right, so that's negation. Let's make a truth table. So just like in 250, here's a table. P is a proposition. And every proposition has a truth value. It's either false or it's true. And I'm going to fill in the truth value for the negation of P. And it will turn out if P is false, the negation is true. If P is true, the negation is false. And that's just a not. It's an inverter. It's a 7404. But it's a truth table. All right, another way we can make new propositions from old is conjunction. Any Schoolhouse Rock fans here? Give me a thumbs up. Go watch Schoolhouse Rock. Go Google conjunction junction. What's your function? Conjunction is an and. And we can take the conjunction of two propositions and get a new proposition, which says P is true and Q is true. All right, so P can be the proposition, my name is Nick. Q can be the proposition 1 + 1 = 5. P and Q is the proposition, my name is Nick, and 1 + 1 = 5. Okay, it's a straightforward logic operation. And I can make a truth table for this. So for a pair of propositions P and Q, exactly one of four things is true. They could both be false. P could be false, Q could be true, P could be true, and Q could be false. Or they could both be true. Well, if P and Q are both false, can P and Q both be true? Absolutely not. If P is false, can P and Q be true? No, because P is false. And if Q is false, can P and Q be true? No, because Q is false. But if P is true and Q is true, what can we say about the statement P and Q? It's true, right? P could be the proposition, my name is Nick. Q could be the proposition, today is Wednesday. This is the proposition, my name is Nick, and today is Wednesday. If each of those things is true, then this conjunction is also true. And that's a good old and statement. Let's see, Christian, yeah, conjunction junction. Wasn't that technically an advertisement for another animation, but wasn't actually part of Schoolhouse Rock? I thought it was part of Schoolhouse Rock. I could be wrong, but that's when I saw it as a kid. Along with I'm Just a Bill, and all that stuff. But I'll check that. Alright, so disjunction, which is an or. P disjunction Q means P or Q. So P is the proposition, my name is Nick. Q is the proposition, 1 + 1 = a zillion, right? P or Q is true. My name is Nick, or 1 + 1 = a zillion. Well, that proposition has a truth value of true. So this is our familiar or operation. If both P and Q are false, the disjunction will be false, but otherwise it will be true. So we can form new propositions out of old ones. All right, and these are three primary ways that we do this: negation, conjunction, disjunction, and or not. Or not and or. And this is what we sometimes call an inclusive or, right? If P and Q are both true, then absolutely P or Q is still true. It's not an exclusive or, even though in English often we mean XOR. We mean P or Q can be true, but not both. Okay, but we can write a truth table for an exclusive or. And now we're back into heavy engineering 250 land. So it looks like an inclusive, except the last row has to be false. So someone's commenting that it would be nice if there was consistency here. There kind of is, because this and symbol kind of looks like an intersection symbol, and this or symbol kind of looks like a union symbol. Right? And this is also the and the or that we use in engineering 250. So it all kind of is the same thing. And the negation is just weird. I think the negation symbol was probably around before typewriters, because we don't have that on most typewriters, although when I was in school we did, because there were some languages that used that symbol. All right, so this is one way to create propositions from other propositions. Okay, negation, conjunction, disjunction. Everybody okay with those so far? Because we're going to go into the weirder stuff. All right, so the next thing is conditional statements. And everything we're doing here is making new props from old. So again, let P and Q be propositions. Here's a new proposition. P arrow Q is the proposition if P, then Q. So it's a conditional statement. So assuming P and Q are propositions, this is the proposition if P, then Q. And it mostly works the way we would expect from reading this in English. It means that if P is true, then Q is true. Okay? This is not necessarily a true proposition, but it is a proposition. Okay? And this is called the hypothesis. And this is called the conclusion. Okay. Let P be the proposition I buy a lottery ticket today. Let Q be the proposition I am a millionaire tomorrow. So P is the proposition that I buy a lottery ticket today. Q is the proposition I'm a millionaire tomorrow. So what is this? This is the proposition if I buy a lottery ticket today, then I am a millionaire tomorrow. It's a completely valid proposition. It's probably not a true proposition, though. Okay? But writing this and saying this is a proposition has nothing to do with the truth value. Okay, it's just a new proposition. P could be the proposition my name is Nick. Q could be the proposition 1 plus 1 equals 5. This would be the proposition if my name is Nick, then 1 plus 1 equals 5. It's not a true proposition, but it's a proposition. So let's look at the truth values for conditional statements. And this gets a little bit weird, but that's okay. Here's a proposition P. Here's a proposition Q. Here's a third proposition which says if P then Q. And we have 4 possibilities. Alright, so let's address these one at a time. First of all, suppose that P is true and Q is true. So my name is Nick, 1 plus 1 equals 2. And this says if my name is Nick, 1 plus 1 equals 2. Well, for this to be true, any time that my name is Nick, 1 plus 1 must equal 2. Okay, well my name is Nick, and guess what? 1 plus 1 does equal true. So this conditional statement is true in that case. And we're not talking causality here. It's not because my name is Nick, 1 plus 1 equals 2. This is simply saying if my name is Nick, then 1 plus 1 equals 2. And that's a true statement because, 1 plus 1 equals 2. Now, if I said, if my name is Jennifer, then 1 plus 1 equals true. 1 plus 1 equals 2. That's a different matter. Okay, we're going to come to that one last. Let's try this row up here. So let me give an example. Let P be the proposition. My name is Nick. Let Q be the proposition. 1 plus 1 equals 5. So P arrow Q says, if my name is Nick, then 1 plus 1 equals 5. And that proposition is false. And we know it's false because my name is Nick and 1 plus 1 is not equal to 5. And so this is absolutely false. Alright, and it has to be false because this statement is saying if P is true, then Q is true. Well, in this particular case, P is true, but Q is false. So this conditional statement fails. It's false. Alright. So let's try this second row. Let P be the proposition. My name is Jenny. Let Q be the proposition. 1 plus 1 equals 2. This statement is saying, if my name is Jenny, then 1 plus 1 equals 2. So what do you think? Is that proposition true or false? Throw some votes in the chat. So we got some false votes, more false votes. Got our first true vote. It feels false, right? And I think it feels false because we're thinking causality. Like maybe if I change my name, 1 plus 1 will be equal to 2 now. Or maybe it makes no sense because this hypothesis is false. Maybe something's undefined, right? But it turns out this is actually a true proposition. So if something false, then something that's true, that's a true statement. Okay, and that feels a little weird. It feels counterintuitive. But what this statement is saying is that if this thing is true, then that thing must be true. Well, if this thing turns out to be false, right, we have not violated this assertion that if P, then Q. All right. What's really going to be disturbing is that in this case where P and Q are both false, this is also true. So if cows can fly, then 1 plus 1 equals 5. That is a true proposition. This is logically true. If cows can fly, then 1 plus 1 equals 5. Okay, so how can we make sense out of this? Let me try a different pair of propositions, and let's see what we come to. So let P be the proposition, and let Q be the proposition. So I'm going to make a pair of propositions. First proposition is going to be x is less than 5. And Q is going to be the proposition x is less than 10. All right. So 4 possibilities for P and Q, right? So let's think of, for example, x is equal to 0. Okay. Proposition P is true. Proposition Q is true. We're claiming that if P, then Q is also true. But let's see what P implies Q actually means. P implies Q says, if x is less than 5, then x is less than 10. Just from what we know about numbers, does this feel like a true proposition? If x is less than 5, then x is less than 10. Does everybody pretty much agree that's a true proposition for any number x? Right? I mean, that's how less than works. If something's less than 5, it's definitely less than 10. So if, for example, I pick an x which is 0, right, we know this proposition is true without doing any work. Okay, suppose I pick an x like 7. We know this proposition has got to be true. Oh, sorry. 7. So where it's not less than 5, but it's less than 10, right? We know this proposition has got to be true. And if I pick something like, 25, where x is not less than 5 and x is not less than 10, this proposition has still got to be true. We can't change the truth value of this fact by just picking some particular number x. I mean, we've already decided for any number x, this proposition is true, whether x is 25 or 7 or 0. Right? So here it's greater than 5 but less than 10, and this is still true. If it's less than 5, it's less than 10. Well, just because I picked an x which was not less than 5 doesn't mean this statement suddenly falls apart. It's still a true statement. Now, the one weird case is right here. And we've said that this proposition should have a value of false. But there's no x I can find for this case. Right? There's no x which is less than 5 but not less than 10. If there was, right, then this statement would be false for that particular value of x. But it turns out there's no x that satisfies p, that makes p true and q false, right? So anyway, that's a motivational example for why these two rows turn out to be true. And and it is counterintuitive, right? P is false, Q is false, but it turns out if P, then Q is true. And this is just one way to sort of try to think about that, right? Think of this case where, for example, x is 25. This is not true, this is not true, but this is still a true statement, right? The fact that my hypothesis is false doesn't force the if-then to be false. And this is an example of a way to see that. Beyond that, we just kind of need to take this on faith for now and work with it, and one day it will seem obvious, perhaps, or at least more comfortable. All right, so that's conditional statements. So conditional statements get into this whole language issue a little more. So let's look at forms of conditional statements. So if P, then Q. Sometimes we'll write if P, comma Q. That's a little sloppy, but you'll see it. We'll also see P is sufficient for Q, which means the only thing that has to be satisfied for Q to be true is P. P is enough for Q to be true. We might say Q if P, meaning Q is true if P is true. Q unless not P. This says Q is always true unless not P is true. In other words, P is false. And our intuitive understanding of if-then goes out the window with all of this, right? So if it is sunny, then 1 plus 1 equals 2. This is always true, right? Why is it always true? Because if we look at our truth table for conditionals, anytime the hypothesis is true, which is anytime the conclusion is true, which is here or here, the conditional statement is true. Doesn't matter if the hypothesis is true or false. So if it is sunny, then 1 plus 1 equals 2. This is always true. Okay, I'm going to get a little sloppy with this. I'm going to call this P, and I'm going to call this Q. So if P, then Q. This is a true statement because the conclusion is always true. But now we can translate this into saying 1 plus 1 equals 2 if it is sunny. Well, that's true. We're not saying it depends on it being sunny, but you know, it's sunny, hey, 1 plus 1 equals 2. Turns out if it's rainy, 1 plus 1 still equals 2. We're not saying that's not the case here. 1 plus 1 equals 2 unless it's not sunny. That doesn't mean 1 plus 1 is not 2 if it's not sunny. We're saying we can guarantee 1 plus 1 is 2 unless it's not sunny. If it's rainy, we don't know. But it will turn out 1 plus 1 still equals 2. But this is saying, all it's saying, if it's sunny, then 1 plus 1 equals 2. Okay, here's a real noodle baker. A necessary condition for P is Q. A necessary condition for P is Q. A necessary condition for it to be sunny is 1 plus 1 equals 2. So what the heck kind of world are we building here, right? A necessary condition for it to be sunny is 1 plus 1 equals 2. Well, we can safely say that as a true statement because 1 plus 1 is always equal to 2. Okay, but it's not causality. But it sounds weird. It sounds like if somehow we change math so 1 plus 1 is not equal to 3, then it's never sunny again. Okay, that's not what this is saying. This is purely just looking at logic values. It's purely just playing with truth tables. But if you start thinking about it late at night and drilling down into these things, you'll find all kinds of things that seem bizarre, okay? They are bizarre because it's a very formal way of treating something that we normally deal with internally in a very intuitive way. And those come at odds with each other sometimes. All right, so we can form this new proposition, if P then Q, from simpler propositions P and Q. Let's see, someone posted an example which said, if it's rainy, the ground is wet. If there's no rain and the ground is wet, that's fine. Someone probably had a sprinkler or something. And if it's rainy and the ground is wet, well, obviously, but if it's rainy and the ground isn't wet, there's something wrong. Yeah, that's a good way to think about it. So you can look at that in chat and write out your propositions for rainy and wet, R and W, and fill out the truth table. All right, so if P then Q, that's a new proposition we made from old propositions. We can create new propositions from this. We can create the proposition if Q, then P. That's another proposition. It's a declarative statement with a truth value. That has a particular name. It's called the converse. So you get the converse by simply switching around the hypothesis and the conclusion. Another thing we can form is the inverse. The inverse says, if not P, then not Q. We can also form something called the contrapositive. And that we get by doing both, taking the inverse of the converse, or the converse of the inverse. So the contrapositive says, if not Q, then not P. So let's look at some examples of this, and I'll use reasonable sounding propositions for this. Let P be the proposition, today is Wednesday. Let Q be the proposition, we have class today. So P arrow Q, if P then Q says, if today is Wednesday, then we have class today. Okay, what's the converse? If Q then P, that's the proposition, if we have class today, then today is Wednesday. Is that a true proposition? First of all, if P then Q, that's a true proposition. If today's Wednesday, we have class. Okay, what about the converse? If we have class today, then today is Wednesday. Is that true or false?
False.
Yeah, that is absolutely false. Because we could have class on Friday. We could have class on Monday. So just having class doesn't mean that today is Wednesday. Could be a Monday or a Friday, so that's false. What about the inverse? If we don't have class today, then today is not Wednesday. If we don't have class today, then today is not Wednesday. Oh, I did that backwards. That's the contrapositive. Let's do the inverse first. So if today is not Wednesday, then we don't have class. So if today is not Wednesday, then we do not have class. Is that true or false?
False.
That's also false. If today's not Wednesday, it might be Monday, we might still have class. So that's false. But this one that I started to do a minute ago, which is actually the contrapositive, if we don't have class, then it's not Wednesday. That turns out to be true. If we don't have class today is not Wednesday. Since we have class every Wednesday, if we don't have class, it cannot be Wednesday, right? Assuming that this statement is true, that if today is Wednesday we have class, this contrapositive has also got to be true. If we don't have class, it can't be Wednesday. Because if we don't have class and today is Wednesday, then this original statement is false. Because this says if it's Wednesday, we have class. So it turns out that if P then Q, and if not Q then not P, these are equivalent. They're logically the same truth value, always, guaranteed. The converse and the inverse may or may not have the same truth value as the original conditional statement. Could turn out they have the same value. This could be 1 plus 1 equals 2. This could be 2 plus 2 equals 4. And, all four of these statements will be true. But in general, the converse and the inverse, not the same statement as the original conditional. But the contrapositive is exactly the same. And that's going to be really useful when we're doing proofs, because a lot of times we can take a statement, turn it into its contrapositive, and then do something with it that we couldn't easily do with the original statement. All right, one more thing to talk about biconditionals. So this is a biconditional. And this is a shorthand for saying if P then Q and if Q then P. So it's a two-headed arrow, and it's basically saying if P then Q, if Q then P. And we can also interpret this as saying P if and only if Q. And we'll abbreviate if and only if with IFF. That's a standard shorthand. We can also say P is necessary and sufficient for Q we can say Q is necessary and sufficient for P. So that's a biconditional. P if and only if Q. And it really just means literally if P then Q, and also if Q then P. So P could be the proposition today is Monday, Wednesday, or Friday. Q could be the proposition we are in class. Or we have class today, right? So if it's Monday, Wednesday, or Friday, we have class. If we have class, it's Monday, Wednesday, or Friday. That's an if and only if. So we can make a truth table for some of this stuff. We already did the truth table for if P then Q, and we saw that this was true in all cases except where the hypothesis is true and the conclusion is false. Any other case, the conditional statement is true. And so if Q then P will be true in any case except where the hypothesis Q is true and the conclusion is false. And so the biconditional is the conjunction of these two expressions, which will be true, false, false, true. And for whatever reason, that's an exclusive NOR. All right, questions? This is a lot of stuff, but it's a pretty good stopping point because I want the stuff to kind of bounce around your brains for a few days, and then we'll dig into doing some mechanics around this. But the concepts can be kind of tricky at first. All right, so take a look at your homework assignment. Bring questions for that on Friday. But your homework's basically around writing propositions, taking sentences with, say, if-thens in it, or conjunctions or disjunctions, and writing it in terms of simpler propositions, doing some truth tables, and we'll play around Friday with proving some statements using truth tables. Again, it's another rehash of Engineering 250. It's another visitation of membership properties, membership tables. So question, why is the second case from if Q then P false? So if Q then P, because the hypothesis is true and the conclusion is false. But this statement says if the hypothesis is true, then the conclusion must be true. Well, in this case, the hypothesis is true, but the conclusion is false, so the conditional statement is false. It's exactly the same as why we have a false here. We've just switched Q and P around. If that didn't answer it, shoot me an email and we'll talk about it more. All right. Cool. I will leave it there for now then. Have a good rest of the day, and I will see you probably in 224 tomorrow, or else in 215. Office hours tonight at 5. Come by if you got questions on any of the stuff or on the homework. Otherwise, I will catch you next time.